Hi all, I'm Vikram. I'm a graduate student at Columbia University. So first half of the talk will be given by Sarthika. I'll hand over the mic to her.
Hi everyone. So I'm Sarthika. I'm a software engineer at Microsoft, and today we are going to talk about parallel and distributed programming and using a standard known as message passing interface or MPI. Yeah. So first, let's quickly go over the agenda. We will start with a quick discussion on the key differences between concurrent and parallel programming, followed by a detailed discussion on the crux of our presentation, that is MPI, and how to use it in Python. We will see how to use MPI for both parallel and distributed programming, along with some examples. Then we will have a quick glance on what are the things to consider while writing parallel code and what mistakes to avoid, and this will give us an overview of what are the best practices to follow. In the end, we will have a fun trivia and a Q&A session, and we will conclude the presentation with that. Right. So let's first see how performance of programs can be improved. So there are two ways. One is concurrent programming and one is parallel programming. If you see the figures here, there are two tasks that need to be executed, T1 and T2, and they have both been divided into multiple pieces. In the left figure, you will see that T1 and T2 are interleaved, but at any given point of time, only one of them is getting executed. While in the second, in the right side figure, we will see that T1 and T2 are getting executed simultaneously, like they are getting executed at the same time also. So the left one is known as concurrent programming, while the right one is known as parallel programming. Concurrency is a broader term, but here we are using it to mean something specific, which is the left one. So this is the basic difference. We are using the words interruptibility and independentability here. These are not actual English words, but they do a good job in explaining the difference between concurrency and parallelism. Yeah, so as previously explained, concurrency is the execution of multiple instructions within the same time frame. So for example, we can consider if there is a queue at a bank and there is a separate queue for senior citizens, and there is only one teller. So the teller will alternatively switch between the two queues and making like both the queues progress together, but at a time only one queue will progress. So that can be taken as an analogy to understand concurrency. And it's a semantic property of the program, which means that we have to consider the design of the problem at hand. Like the task should be able to switch between themselves, and we have to design it in such a way. Also, it increases the responsiveness of the system because it allows the processes to share resources. And concurrency can be achieved using threads, processes, or asynchronous programming. We will not like dive deep into these things because our focus will be on parallel and distributed programming. Yeah, so whenever you try to execute a CPU-intensive program on a thread, when the runtime switches to another thread, there is the previous thread gets paused. So there is no performance benefit over like executing this outside of the thread. So to do this, like to avoid this limitation, we will use processes instead of threads, and we will move on to parallel programming. Parallelism is actually the execution of multiple instructions at the same time. So if we take the same example as the queue at the bank, now there will be two queues and there will be a teller for each queue. So both the queues will be progressing together and not waiting for each other. So this is how like you can understand what is the difference between concurrency and parallelism. And apart from designing the code, it also involves like designing the hardware level, because multiple computing resources are needed to like the separate cores or separate processors. So if there is, if we are using separate cores, that is known as parallel programming, and the latter one is known as distributed programming. And it can be achieved using MPI, OpenMP, and pthreads, and we will be discussing MPI today. Yeah. So message passing interface. So MPI is basically a language agnostic model which is used for writing message passing programs. So message passing, it's basically a protocol to communicate and to like to allow actions to communicate with each other and without actually sharing the address space. So MPI is a protocol and message passing is the standard. So, and MPI is also SPMD. Basically, single program is executing on multiple processors, and each instance is aware that what part it's doing computation on, and in the end, these results are combined to give the final result. Yeah. So, but what's the catch? Catch is like it's difficult writing programs in MPI because you will have to all synchronize and see that the processes are eventually completing and they are actually our results are getting merged. So we will now see how we will use MPI. First of all, let's see on let's focus on some of the basic terminologies that will be used in the future slides. First is distributed memory or shared memory. So this you might have guessed, like if there is a separate address space, then it's distributed memory, and if there is a common address space, it is known as shared memory. And then a process is an instance of a program that is running on a computer. Then there comes communicator. So communicator is an MPI concept. It basically is a group of processes that are currently executing, and a rank is used to identify those processes in a communicator. Size is the total number of processes in the communicator. So it's rank is zero-based indexing. So rank goes from 0 to size minus 1. And a process can exist in multiple communicators and can have different ranks in each. Also, MPI provides a default communicator known as MPI convert, and it includes all the processes in execution. You can write your own custom communicators also, but this is the default one that MPI already provides. Yeah, now I would like to hand it over to Vikram.
Thank you. So now we'll come to support for MPI in Python. So we already know that C++ and Java, they have had bindings for MPI since a long time, C++ especially. So MPI for Py is a library which provides bindings in Python. So now you can write parallel codes in Python. It is a really cool library because it's very fast. It's near C speed. It uses pickle-based communication, so some of you also might know pickle in general. And the way you do is, like, if you have a program, MPI program, the way you write it is using this MPI exec command. You specify the number of processes that you need to have, and then you use the M flag, and then you write your Python file which you need to execute. So this Python file itself needs to have some commands in general, which we'll discuss later. But basically, what would MPI have? So if we think about it, if we have a couple of processes communicating with each other, basically we would need routines for communication. And communication here would mean like sending and receiving messages. So processes should be able to send messages to other processes, and those other processes should have some way of receiving those messages. Moreover, there needs to be synchronization. That is, what if all the processes need to pause for a certain time so that all computation occurs? So that's where we need synchronization. And as Sarthika mentioned, we have communicator creation. So these concepts would be in advanced MPI, that you need multiple communicators and multiple groups of processes. And some advanced features are also supported, like if I need to send custom user-defined objects to other processes, or I want to do parallel I/O, for example. So we would not touch on these. We would just stick to sending and receiving messages in different ways. So now let's see how MPI looks in action. So hello. Yeah. So imagine you have 4 processes, and these can be multiple processors on a single machine, or these can actually be 4 different machines connected together in a topology. But now we're generalizing it, so let's call them 4 processes. So one of the process P0 is, we'll call the master process. So it has a hello world.py file. When I execute MPI exec command on this, and I specify, like, I want to execute it on 4 machines, what actually happens is, you can imagine it being something like this. Hello world.py actually goes to all of these machines, and they all execute parallelly. And then how would I determine, like, who to send the message and who receives the messages? So we'll come to that later. But this is how you can imagine MPI to be in action. So let's come to our first communication protocol that we have, that is the comworld.send. So comworld is the default communicator that we have. So here we have 3 processes, one with rank 2, one with rank 7, one with rank 5. 2 has a bunch of data, and it needs to send it to other processes. So we have the send method. Let's look at the signature. So what all do we need? We need what data do I need to send, whom do I need to send it to, and there's an optional parameter called a tag. So we'll go one by one. So we like if 2 has a data and let's call it obj. So 2 sends this data. If 2 wants to send this data to 5, it will execute something like send o1 5 comma 1. So 5 is the rank of the process number 5, and the tag is basically something like if 2 wants to send multiple messages to 5 and 5 needs a way to decode that, okay, what's the first message, what's the second message, so it can use the tag. So it first sends it with 1, it sends another data with 2. So 5 knows that, okay, I received O1 first and received O2 later. But tag is optional. So 2 can also send something to 7 without a tag if 7 does not need to know like what's the exact order of my messages. So this is an additional parameter. So this is our first method. Some things to note here that first, it is a blocking call, meaning unless and until someone receives a message by executing the receive method, 2 would be stopped on sending it. So this has a caveat, we'll come to it later, but basically it's a blocking call. And the caveat here is that actually, in some cases, if the data is very small, it fits in the buffer. What can happen is it can finish executing even before it is received because it's stored somewhere in the buffer. It's not important for our discussion, but I just would like to mention this. So the other method is the receive method. This is the counterpart for the send method. Again, what do we need here? We need where do I store the data that I receive? Is the buffer parameter. Then whom do I receive the data from? That is the source parameter. Again, you would note that this is optional. We'll come to that later. We have a tag and we have a status. All these 3 parameters in the end are optional. So why are they optional? First, before that, let's just look at how it would look in practice. So like if 2 would like to receive a message from 7, it would do like so. It receives 3 messages from different processes. Now, when I say the source is optional, what it means is that if I do not specify a source, so if 2 executes something like receive B1, what would actually happen is any process that has to send some data or that has executed send, 2 would keep that data without caring about who sent that data. So that is why the source is optional. And the status flag is like, it stores some metadata. So like the status would have data like who sent me the data and like some additional metadata parameters which you might need for complex programs. Some more helpful methods, as Sarthika mentioned, we have the size and rank. So the size in occasionally or like almost in all the MPI programs, you would need to know how many processes are there in my pool. So you use the get size method. You also need the get rank method. So if there are 5 processes, I need to know what is the job that I need to do. For that, I need what rank is it. So ranks are assigned randomly in the beginning of the program. So I would need to know what rank I have. So it goes from 0 to size -1. Now let's look at our first MPI program. So in all our programs, when we learn a new language, we have the Hello World program. But because we are in the parallel world, we have this Hello World program. What this program is trying to do is there are 5 processes, and each process basically sends the string hello world to a process with rank 0. And the process with rank 0 is just printing out all the hello world. So the first few lines, these are standard. So like if you import it, you initialize the communicator, you get the rank, and you get the number of processes. So this rank and number of processes would be used later. So this is where the divergence happens. That is, based on my rank, I can do different things. So if my rank is 0, what I'm doing is basically trying to receive messages from all the other processes in my communicator. If my rank is not 0, that is my rank is 1, 2, 3, or 4, I just send a data hello world to the rank number 0. So 4 processes send this data to process 0, and process 0 receives these messages and just prints out. So you would have an output something like this. Process 1 says hello world, and so on. So this is the first simple program in MPI. Now we know how to send and receive messages. Let's move to something more complicated. That is, if I want to calculate the area under a curve. So this is all this is also a simplified version, but like an integration, what you do is if you want to compute the area under a curve, divide it into small rectangles, compute the area of each rectangle, and then sum it up. Do this using, yeah. What we need to do is, the first few lines are the same, rank and size. Then we go to the start process. Basically, the start and end is the coordinates of my curve. It goes from 0 to 8. Interval is basically each process would get an interval of 2. That is, process 1 would calculate the area of this thing, this rectangle, process 2 for this, process 3 for this, process 4 for this. So find area is a method which we assume, given the start coordinate and the end coordinate, it can compute the area under this curve. So in this case, it's just a rectangle. But imagine if this would be some weird shape, and you would need some more computation for doing that. So this basically find area method would calculate the area. So each process has its own rank. Each process would calculate the area of the chunk assigned to it. And it would store in a variable called local area. Now, again, we do the same thing. We do the orchestration and the distribution of work. So if my rank is 0, I first calculate my own area. But in addition to that, I also receive messages from all the other processes of the area of their chunk, and then add it up together in a variable called total area and store it. So basically, all the other processes can compute their own area. They already did it here, but they need to still send the data to the process 0. So they do that here. So we would have output something like this. Each rank would calculate their own area, each process, and they would send the area to rank 0. And in all, at the end of the program, rank 0 would have the total area stored in this total area variable. Now let's, like this was a lot of for loops and like a lot of send and receive messages. So there are some complex, there's slightly better communication paradigms in MPI which we can discuss. So these are called collective operations. So the first collective operation is broadcast. So what if one process needs to send the data to all the other processes in the group? What we can do is write this bcast call, which basically does what data do you need to send and who needs to send it. So this call is called for all the processes, but only root is equal to 0. So basically, only process with root is with rank is equal to 0 would send the data to all, and for all the other processes executing this, they would have the data sent to them by rank is equal to 0. Another one is the reduce method, in which if I have a bunch of objects, for example, you might be aware of map reduce, for example. So reduce basically collects a group of data and reduces it to a smaller number. So if we have like an array of variables, reduce is something like what is the sum of the array. This is just an example. So reduce basically takes a bunch of data, reduces it to one single number. And this is especially helpful. For example, in this area, example, what we needed to do is we needed to reduce a group of numbers, that is the area of each individual chunk, and then sum it up. So this can be thought of as a reduce operation. So now our code becomes very simple using the reduce method. So this is just for reference, but all the for loops can be like basically collapsed into one single line of code, that is com.reduce local area. So rank 0 would have now the total area stored, total area for all of these processes. I do not need to specify that how I need to reduce, because the default reduce operation is the sum operation. So in this case, MPI would know that I need to sum up all the areas. So yeah, this is one example. Then let's come to distributed programming. So as I mentioned in the beginning, we can have multiple cores running the same MPI program, or we can have multiple nodes running the same MPI program. So if you have a bunch of machines connected in the network, what you do is you specify a machine file in which you specify the IP addresses of all the machines in your network, and then execute something like this. You specify the machine file here, And then MPI would know like all the processes that need to do the communication, all the nodes that need to do the communication. Now we are trying like on the end of the talk, so we should consider these things while writing MPI programs. So the first one is not everything can be parallelized. So sometimes some programs are inherently sequential. You do not need to parallelize them. They would perform worse than they need to. The second is think about the paradigm that basically when you write MPI programs, you need to consider how do I chunk my data, how do I send the data, how do I receive the data. So work it out before you actually write it. The third one is first it's a good practice to have a serial implementation of your program first and then jump on to the parallel program. It becomes much more easier. The last one is, the fourth one is basically that you need to test your MPI program a lot, and debugging is especially painful because you need to not only debug one program, you need to do multiple simultaneously. Then the next two are like don't optimize prematurely or unnecessarily. Sometimes those optimizations might not work. For example, if you need to do something very simple, there's no need to write like MPI program for that. It's like 100 lines of code just for like minute speed up. So sometimes that does not matter. Optimize communication over computation. So if you have a choice of optimizing, of either doing communication or doing computation, because communication is slower, slightly slower, you can always prefer to do computation over communication. And like the same goes with optimization. The next one is interleaving. So traditionally, you would see a lot of MPI programs are interleaving between like doing some communication, then computation, then doing communication, then doing computation, and so on. And like if we have a bunch of data to send, we can always put the data together and send it in one go rather than doing multiple transfers. Using MPI collective operations. So as I said, doing a broadcast is more optimal compared to doing sends in a for loop. And there are multiple versions of MPI. So when you begin writing MPI programs, it's best to do your research and finding out the right MPI versions. Now, because we do not have a lot of time, I'll quickly go through some of our trivia questions that we had. So I'll just display the question and then talk about it, whether it's true or false. So the first one is that the number of processors should be the same as number of processors. So this is false. I can even write MPI program on a single process, but with the parameter as 4. So what it does is it executes executes the same program 4 times on the same core, same node. Then MPI broadcast is just a replacement of send and receive. This is also false because MPI broadcast is actually more optimal than doing a bunch of sends and receives. The main library for MPI in Python supports both Python 2 and 3. This is true. MPI can handle communication between processes using shared memory. So this is false because it uses distributed memory and not shared memory. The size in MPI is the number of processes in an MPI communicator. So this is true. It gives the total number of processes in my communicator. MPI can be used for network communication in Python. This is false. It's not for network communication. It's for like data transfers between processes in a distributed or like on the same machine or on a bunch of machines. So that was all from our side. If you have any questions, we are happy to take it.
Prova. Okay, this works. Okay, thank you very much both for your great talks. So we have a few questions, so I don't think we have time to address all of them. So let's start with the first one. The question is, how does MPI 4Pi perform in comparison to the multiprocessing library?
Yeah, so there are both of these are like good ways of writing parallel programs. But for this talk specifically, we wanted to focus on MPI because there's already a lot of support for MPI for C++, for example. I do not know the exact performance gains in general, but I assume it to be very close. But this talk, we focused on MPI just because it's already very popular in the C++ community.
Okay, second one is it possible to share not pickable objects between processes? So, or to share memory addresses and load them in another process?
Share memory address. What else possible?
I think I'm not aware of this.
I think it's not possible.
So basically the object you share between the process is something what is pickable. I guess it's something very trivial.
Yeah.
But let's assume you load something more complex into the memory, which is not necessarily pickable.
Yeah.
Is it possible to share that object between the processes?
Yes.
So it's not pickable, it's possible to share.
Yes, yeah, we can do that. And there's also support for like if you can marshal an objects, you can also do that. But
I assume I cannot marshal, I cannot pick it.
yes.
That's the memory address which I have.
Okay, I'm not completely aware of this. Sorry.
Okay, last couple of questions. Is there a best practice to share binary data between processes in the scenario producer-consumer?
If you mean like primitive data in general, like one thing to optimize for is always using collective operations, if that's what the question meant. But yeah, basically we can do that.
Okay, I think we have time for the last one. Then you can find them outside to ask. So which visualizing tool I can use to draw cooperative execution of all my coroutines in one thread? And how about parallel processes in threads?
So yeah, so there are libraries like one is IPython, I think, which provides visualization of what all is actually getting executed like across threads and processes. So you can try that. Yeah.
Okay, time is over. So thank you very much, to the speaker.